Hello students, welcome again. I am Ashwini Kumar from Department of Applied Sciences, David Chalandar. Today I am going to give you a lecture on numerical methods to find roots of algebraic and transcendental equation. So you should know first of all what is a root. Suppose y is a function of x. Then for this y, a value alpha is known to be the root if the value of fx at that point x equal to alpha is 0, right? So alpha is known to be the root. So now next thing we should know that how many roots of a function will exist. So roots may be finite or may be infinite. So a function, an equation may have finite roots if that equation is a polynomial. But if the equation is a transcendental equation, then that equation may have infinite roots. I have given one graphical presentation that what is root. So you can see that the red line indicates the function and the these blue dots represents the roots, right? So the root is clear that the point at which the value of function is 0 is known to be the root. So now some preliminaries. You know, in your lower classes you have find the solutions of quadratic equations, biquadratic equations, cubic equations as well. So all those solutions are easy to find. But when an equation is having a degree at least 5, right, more than 4, so in that case to find root is very difficult, very challenging. Similarly, if we have some transcendental equation, so first of all you should know that what is transcendental equation. An equation which involves special functions like sine, cos, log, exponentials, etc. All those equations are known to be transcendental equations. So if if suppose we have to find root of transcendental equation, then it will be very difficult for us, right? So we have learned that if we have an algebraic equation means polynomial. So if we have an algebraic equation with degree more than 4, and if we have transcendental equation, finding root is a challenge for us. So even in your lower classes, if you have learned Ferrari and Descartes method, those are also not easy. These Ferrari and Descartes methods both finds the roots for cubic and biquadratic equations. So we have learned that finding root is a challenge. Now, what numerical methods do in that case? So numerical methods give an algorithmic approach, give a, you can say, easy approach to find those roots. So now in numerical methods we have two types of approaches to find root. So these are, first we have bracketing approach, and another one is called open-end approach. Now what are these? In bracketing approach, what we do, we take a bracket, you can say an interval in which our root lies, right? So these two methods, namely bisection method and false position method, both follows bracketing technique. Now in an open end method technique, the method uses only one value sometimes, or sometimes it may take two values as well, but the approximation may not lie in the bracket, in that bracket. So one thing I want to clear that in bracketing method, every time the new approximation lie in between our bracket. So that's why they are called bracketing method. So Newton-Raphson is a method of open method type. So this is one, you can say, some rules about bracketing method. When we choose a bracket, for example, A is our lower end and B is our upper end, then A to B is our bracket. So if we have a bracket in which our root lies, then definitely in that bracket at least one or more root lies. So we can make a general rule about this, that if we have a function negative and at b the function is positive, then definitely the roots will be odd in number. Means to say, either the function may have one root or it may have odd number of roots. In the second rule of bracketing method, if you have a bracket a to b but both the ends at a, means to say at a and at b, both the values of function are positive, then definitely the in that bracket the number of roots must be even, or there may not be some root. That means the number of roots will be even in number. So we have two types of brackets and we have two types of rules. If at a the function is negative and at b the function is positive, or vice versa, then there must be an odd number of rules. And the second rule is that if both the ends, means at a and at b, the function value is either positive at both sides or negative at both sides, then the number of roots will be even in number. So these are the two rules for bracketing method. So now there sometimes there exists some flaws, some violations in bracketing method. These violations are due to either multiple root existence or some discontinuity existence. So you can see, if one multiple root exists, multiple means to say either it may be double, triple, or uh, with a root of more multiplicity, that is called multiple root. So here I have taken one example of double root. So you can see at a the function is positive and at b the function is negative, but the number of roots lying in between this a to b is 3, right? Now in this case you can see the discontinuity appears here. So this is the point of discontinuity. So in a and b both the ends are positive, means to say sorry, both the ends are negative, means to say this is a second type of bracketing rule, that fa and fb product is positive. So you can see the number of roots are 3, but we have discussed that the number of roots should be even in number. So this violation is because the point of discontinuity occurs in between the bracket, right? So when you choose your bracket, you must take care that there should not be any point of discontinuity, as well as there should not be any multiple root. So this rule is to be adopted by you students when you choose the bracket. Now, when you choose your bracket, you must follow some rules. You can say rules as well, and one more thing you can say, that this improves your bracket. Now, in lower classes, you have learnt about graphical view of some function. What you have done there, you suppose you have a function and then you have done what? You have divided your x into small intervals, small steps, and at every point you have found y and then you made a graph. So this is called graphical view. So this is very helpful when you choose one bracket, right? Because when you have some view, some idea about your function, that where your function has root, then it become easier to find the bracket, to choose the bracket, right? Now, to improve your bracket, to make your process faster, you can use incremental search technique. Now what is this? Suppose you have chosen the bracket 0 to 1, and suppose you are solving your question from bisection method, as you have not done yet, but it's okay, we will do it later. Bisection method, you have chosen bisection method to solve that equation, then it will be sometime very slow, right? Means to say it will take around 20 to 25 to 30 iterations as well. Sometime it happens because of the slow convergence of bisection method. Then at that instant what you can do, you can use incremental search technique to refine your bracket, means to say to improve your speed of the method, right? So now how can you do that? You can do that. Suppose a to b is your bracket, then start from divide a to b in small intervals, and every interval find out the value and choose the smallest interval in which your root lies and discard the other bracket. So in this way you can improve your bracket. So this is one graphical view of open-end method. You can, for simplicity, I have taken the idea of Newton-Raphson because Newton-Raphson is an open method. So you can see this is your x naught initial approximation. In Newton-Raphson we need only one initial approximation. From this initial approximation, at this point we have drawn the tangent, and this tangent where cuts x-axis, this is our new approximation. This is the methodology of Newton-Raphson method. Now again at x1 we have drawn the tangent, and this tangent falls at x2 on x-axis. This is our new second approximation. So in this way we will find the root. So you can see open-end method is very fast as compared to bracketing method. But my dear students, open methods are not always convergent. They may fail. So this is one graphical structure, graphical view of same Newton-Raphson method for your, you can say, for your understanding. Now just see, I have started from point 4 here, right? At point 4, the tangent falls at near to some point 2 value. Now if I again try to find approximation using Newton-Raphson, now just see at this point near to point 2, the slope is not meeting x-axis near to the value. So it is touching very far away from the initial approximation. So this is the flaw in these methods. So open-end methods may not converge always. This may diverge. So this is the flaw. Open-end methods are very fast, but sometimes they can diverge. So this is one summary about bracketing method and open-end method. So I can read it. Bracketing methods have slow rate of convergence, but these are surely convergent, right? So this is one very good characteristic of, you can say, bracketing methods. Open-end methods as compared to bracketing methods are very fast, but as you have seen in your previous slide, that open method may not converge always. So if you want reliability, then you can choose bracketing method. But if you want less time consumption, then you can use the open-end method, but with some precautions. Now in this lecture we are going to study three methods: bisection method, false position method, and Newton-Raphson method. As we have discussed earlier, bisection method and false position method both are bracketing methods, whereas Newton-Raphson method is an